Good afternoon.
We girls don't apply makeup, you know. Oh my Yusuf.
Very good evening, students.
Good evening, sir.
Good evening. Good evening. Let us start with the discussion. Last class we have been discussing about different points in thermodynamics. Yes or no?
Yes, sir.
So we'll continue with our discussion and solve some examples. Then go with the organic chemistry chapter named IUPAC nomenclature and all. So this is the last point of our discussion, that is bond energy calculations. So if you look at bond energy or bond dissociation energy, so delta H you can write as sum of bond energies of all the reactants minus sum of bond energies of all the products. So this was a point of discussion. If a bond energy of various bonds present in the reactants and products are given, then delta H of that reaction then be given by delta H is equal to sum of bond energies of all the reactants minus sum of bond energies of all the products. That means what kind of bonds are there in reactants, what kind of bonds are there in products, all you have to list out and then do it. Heat of hydration, students, how we define heat of hydration? It is the amount of heat evolved when 1 mole of anhydrous salt combines with a fixed number of water molecules to convert it into specific hydrated crystal. So what actually is happening? Like if you take CuSO4 solid plus 5H2O, the copper sulfate will be present as CuSO4.5H2O. That means the ions are actually surrounded by fixed number of H2O molecules. And you have to remember how many H2O molecules are actually hydrated. So if we add a salt, to water or aqua solution, the cations and anions they get hydrated. The cations and anions gets hydrated, and as a whole the ionic crystal gets hydrated. The ionic crystal gets hydrated with a fixed number of H2O molecules. With the fixed number of H2O molecules, and in the whole process, energy is going to be released as stability gained. Energy is released as stability is gained. Okay. Whenever a particular ionic compound is added to water because of hydration, like because of the hydration of these particular ions, the H2O molecules are going to be attracted towards the respective cations and anions, because H2O is a polar molecule which has partial positive charge on hydrogens and partial negative charge on oxygen. Because of this hydration, stability is going to be increased, and that means energy is released, and delta H is going to be negative for that process. That amount of heat released is nothing but heat of hydration. Heat of solution, delta H of solution. So amount of heat absorbed or evolved when 1 mole of substance is directly dissolved in such large volume of solvent such that further addition of solvent does not produce any heat change. Understand this point? Heat of solution may be endothermic or exothermic. What do you mean by this? So you have already added 1 mole of substance, or you have already dissolved 1 mole of substance in large volume of solvent such that further addition of solvent is not going to produce any heat change. In that case, whatever the amount of heat released in that final condition, that is said to be delta H of solution. So CuSO for aqueous gives rise to CuSO for solid plus aqueous, that is water, gives rise to CuSO for aqueous. In this, delta H is nothing but delta H of solution. CuSO for solid plus 5H2O gives rise to CuSO4 dot 5H2O. This is delta H of hydration. The difference here is in the presence of delta H of solvation, large amount of water is added or excessive amount of solvent is there. And MgSO4 plus 7H2O liquid, that is equals to MgSO4 aqueous. And MgSO4 aqueous, whenever we are getting a compound in the aqueous state, that means total or maximum number of solid molecules are added. In that case, we use the term delta H of solution. Whenever we form like fixed number of H2O molecules, in that case, we will be saying delta H of hydration. Similarly, MgSO4 dot 7H2O, so solid plus aqueous gives us to MgSO4 aqueous. Here also we use delta H of solution. Where maximum number of solid molecules are already there, that is said to be delta H of solution. Just a fixed number of H2O molecules are present. In that case, delta H of hydration is used. Is that clear, students?
Yes, sir.
Yes, right. So resonance energy. Resonance energy shows the difference. There are a lot of cases where the molecules are going to show resonance. Resonance is a scenario like when one structure could not explain the complete all properties of the molecule, then more than one structure can be written to explain all the properties, and all those structures are said to be resonating structures. Or you can say when a single structure could not explain all the properties of a molecule, then that molecule is going to show resonance. Resonance always stabilizes the system. So resonance energy shows the difference in energies of a most stable resonating structure and resonance hybrid. Most stable resonating structure and resonance hybrid, between that, whatever the difference in energy is there, that is nothing but your resonance energy. Let us try to solve some examples to get clarity on these perspectives. So first example is calculate the delta H of the reaction. Calculate the delta H of the reaction. CH2Cl2 gives rise to C plus 2 hydrogens plus 2 chlorines. Bond energies of CH and CCl are 415 kilojoules and 326 kilojoules. Solve it, all of you. CH2Cl2 gives rise to C plus 2H plus 2Cl. Calculate the delta H of the reaction. We have to calculate delta H for this particular reaction. Given the bond energies are given to you. All of you do it, students. I'll add the next question. Calculate bond enthalpy of the reaction. Calculate enthalpy of the reaction where bond energies are given. Anyone got the answer for first question? Calculate the delta H of the reaction CH2Cl2 gives rise to C plus 2H plus 2Cl. That means they have said that reaction CH2Cl2 gives rise to C plus 2 hydrogens plus 2 chlorines. So here what you can write, delta H is equals to sum of bond energies of reactants. Whenever the bond energies are given to you have to use the formula. Delta H of reaction is sum of bond energies of reactants minus sum of bond energies of products. So that is equals to sum of bond energies of reactants. What is the bond energies of reactant? CH2Cl2. We have how many CH bonds?
2.
2 CH bonds. How many CCl bonds? 2 CCl bonds. So 2 into bond energy of CH bond plus 2 into bond energy of CCl minus, in the product side we have no bonds, that is it is 0. Free atoms, no? So how much it is? 2 into
1482.
yeah, 415 plus 2 into 326. Try to solve 1482 kilojoules. This is going to be the right answer. So next one is calculate the enthalpy of reaction for the hydrogenation of ethene. Hydrogenation of ethene we have to do. For that particular reaction, we have to calculate the enthalpy of the reaction. Given they have given the bond energies of different kinds of bonds like CH bond, CC bond, C double bond, C, hydrogen, hydrogen single bonds. Right? The solution goes like this, students. Delta H is equals to sum of bond energies of reactants minus sum of bond energies of products. So what is the reaction you have? What is the reaction you're saying? Hydrogenation of ethene. What is ethene? Ethene is CH2 double bond CH2. For that you are adding hydrogen. So you'll be getting CH3 single bond CH3. Yes or no? That means in the reactants what type of bonds are there? In the reactants we have how many CH bonds are there? 4 CH bonds. 4 into bond energy of CH bond plus 1 into bond energy of C double bond C plus 1 into bond energy of hydrogen single bond. These are all the reactants. In the products we have 6 into bond energies of CH bonds, 6 CH bonds are there, plus 1 into bond energy of CC bond, single bond. Substitute whatever the values they have given. CH bond is given as 99. So if you try to calculate 4 into 99 plus C double bond C bond energy 147, 1 into 147. Bond energies of hydrogen single bond 104 minus 6 into bond energy of CH bond is 99 plus 1 into bond energy of CC single bond 83. These many kilocalories, right? These many kilocalories. Do the calculation, students, all of you. So delta H is supposed to be how much? Minus 30 kilocalories. If you try to solve it, approximate value of delta H would be. Check out everyone. Check out the calculation. Minus 30 kilocalories. Next example. Calculate the resonance energy of N2O from the following data. Delta HF naught of N2O, that is equals to 82 kilojoule per mole. N triple bond and bond energy. I am giving different types of bond energies. N double bond N, O double bond O, N double bond O. These energies are given in this fashion. N triple bond N is 946 kilojoule per mole. 418 kilojoule per mole, 498 kilojoule per mole, 607 kilojoule per mole. Do it all of you. Calculate the resonance energy of N2O from the following data. Delta H of naught of N2O is given as 82 kilojoule per mole. So we know this formula, that is resonance energy is nothing but the difference in resonance hybrid as well as the most stable resonating structure. You can also calculate that as resonance energy is difference between delta HF naught calculated minus difference, not minus, delta HF naught calculated and delta H naught observed. How much is delta HF naught calculated? We look at the calculated delta HF naught for this particular N2O. How is N2O formed? N2O delta HF naught they have given. Delta HF naught means what? Not this not indicates standard condition. This delta HF indicates enthalpy of formation. So enthalpy of formation of N2O means we have to produce 1 mole of N2O from nitrogen and oxygen. What nitrogen exists in which states? N2 gas state. Oxygen exists in O2 gas state. To balance it, I have to write like this. N2 plus half O2 gives rise to N2O. So I can write N triple bond N plus half of O double bond O gives rise to N2O. How the structure of N2O can be written? N double bond N double bond O. N double bond N double bond O. So this is nothing but your formula, that is writing the equation as well as indicating all types of bonds. So for this particular reaction, I can write delta H of naught calculated is equals to, this is observed value. This is observed value. Delta H of naught calculated is equals to sum of bond energies of reactants minus sum of bond energies of products. So what are the bond energies in the reactants we have? 1 into bond energy of N triple bond N plus half of bond energy of O double bond O minus 1 into bond energy of N double bond N plus 1 into bond energy of N double bond O. 1 into bond energy of N double bond O. This is the formula. So substitute now everyone. Bond energy of N triple bond N 946, same units, plus half of O double bond O is 498 minus N double bond N is 418. 1 into 418 plus N double bond O is how much? 1 into 607. Try to solve this. You will be getting the answer something approximately 170 kilojoule per mole. So this is nothing but the delta H of naught calculated. So resonance energy, how you can understand the resonance energy calculation, students? Therefore, resonance energy is 170 kilojoule minus what is the observed? 82. That is 88 kilojoule per mole. So this is nothing but your resonance stabilization energy or stability gained. Stability gained is this much. Everyone got it or not?
Yes, sir.
Yes.
Yes, right. So these are the different reactions which we will be having in thermodynamics. So study well and practice more number of problems from thermodynamics. You will get clarity. Just a second. We'll start with the next chapter named as IUPAC nomenclature and isomerism. And you all know from today we are going to start with the organic chemistry. Never miss a class, all of you. Okay? Because once the organic chemistry has been started, you all know it is all connectivity. So we are going to have different types of reactions connected with different concepts. So you should not miss any class. And every concept is important. It's not like one concept is important, other is not. Everything is important. Everything will be having some significance in the reactions. So we have to apply all these concepts, like whatever the IUPAC nomenclature, starting from the nomenclature. Nomenclature is all the IUPAC rules. So we have to remember all those rules and we have to apply. But after the IUPAC rules, we have the isomerism, structural isomerism, stereoisomerism. In the stereo we have cis trans, optical, geometrical. After that we have GOC. In the GOC we have effects, electronic effects, bond cleavages, different types of intermediates and their stabilities, acidic natures, basic natures, ortho effect, steric inhibition of resonance, SIP, Brett's rules, protonization structures. All these points are interlinking with the reactions which you are studying in the upcoming sessions. So don't miss any class, students. So let us start with our organic now. So this is going to be the first concept, that is we have to name the compounds first, classification and nomenclature. So first, how to classify organic compounds or organic molecules. Classification of organic compound. Representation of organic compound is important. First, you should know the molecular formula and the structural formula. Molecular formula gives information regarding the how many types of atoms are there for a specific type. C2H6, C2H6O. So how many types of carbons are there? How many types of hydrogens? Like how many atoms are there? That information is given by molecular formula. Molecular formula just gives information regarding the number of atoms, whereas structural formula gives idea regarding the type of bonds. In that particular molecule like C2H6, what type of bonds are there? That information is given by structural formula. So C2H6 means we get an idea there are 2 carbons and 6 hydrogens. C2H6O means there are 2 carbons, 6 hydrogens and 1 oxygen. Whereas structural formula indicates that C2H6 means there was 3 CH bonds, 1 CC bond and the other 3 CH bonds. Like each carbon involves 3 CH bonds and also the carbon-carbon single bond is there. C2H5OH means here we have CH3, CH2OH. So type of bonds whenever they are included, whenever they are explained, that will give idea regarding the structural formula. Right? Bond line representation. In this representation, CH bonds are not shown. The carbon-hydrogen bonds are not shown. Only carbon-carbon bonds are shown with the help of bond lines. CH3, CH2, 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 CH3 means you can write down 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 carbons are just connected and every connection indicates a carbon-carbon linkage. So this carbon is connected to the next carbon. To this carbon only one other carbon bond is there. So that means this carbon is already having 3 other CH bonds. So because every carbon should have 4 bonds, so this carbon has 1 carbon-carbon bond means the other 3 should be 3 hydrogens are connected. That information you have to know, you have to understand. Look at the second carbon. This carbon is actually connected with already 2 carbon-carbon single bonds. That means it should have 2 other CH single bonds. This carbon also have 2 CH bonds. This carbon also has 2 single CH bonds. And this terminal carbon again has 3 single bonds, 3 CH single bonds. So this is how the structure can be represented. How this structure can be represented? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And in the third carbon, you have 2 methyls. I can place like this. Carbon-carbon bonds are there. CH3, C, triple bond C, CH3. So CH3, how many carbons are there in total? 1, 2, 3, 4. So 1, 2, 3, 4. So triple bond you can indicate in this fashion. The triple bond you can indicate in this fashion. CH3, CH3, CCl, C double bond C OH, CH3. So wherever the different kinds of substances are there you have to mention them. 1 carbon chlorine and 1 COH. Yes or no? CH3, CCl, C double bond C, COH and CH3. So this is the type of linkage which you can show for this particular structure. Is that clear, students? Very simple. How to represent a molecule?
Yes, sir.
Yes. This is just like a basic introduction. We are just representing the molecule in the bond line representation form. Hybridization. Like if you have all the carbon atoms, like carbon atoms in the molecule, if they are connected by a single bonds alone, then how many sigma and how many pi we can say? The number of sigma and number of pi. We can say 4 sigma And you can say how many pi? There was no pi bond, so 0 pi. So what should the hybridization when we have only carbon-carbon single bonds? Hybridization is going to be
sp3
sp3. Bond angle will be
109 28 minute.
approximately 109.5 degree, and shape is going to be tetrahedral. What about this scenario? Just a second. Yes, students. So we are talking about carbon-carbon double bond. Whenever we have double bond, we can say one bond in the double bond or in the multiple bond. One bond is going to be sigma bond. The remaining all are going to be pi bonds. So we have how many sigma here? 3 sigma
Three
bonds are
sigma,
there,
one
and
pi.
one bond is pi ma. Hybridization is going to be
sp2
sp2
sp2 hybridization means what should be the bond angle? Bond angle should
120
be 120 degree, and shape is going to be trigonal planar. Yeah, Ritika, we should, if I mention a carbon-carbon single bond also by the line and carbon hydrogen bond also by the line, then it will be confused or not? If I want to represent this molecule CH3, 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 CH2, CH3, and I am representing lines to every bond, carbon-carbon bond as well as carbon-hydrogen bond. In that case, what my molecule is going to be? So 1, 2, 3 carbons are there. If you try to represent carbon-hydrogen bonds also by lines, is there a differentiation between carbon-carbon single bond line and carbon-hydrogen line? No differentiation here. If I represent like this, then that is not a correct way to represent the molecule. Understood or not?
Yes, sir.
Yes. Only CC bonds are represented, and C double bond C, any other substituents like Cl, halogens, or OH groups, or a triple bond, they have to be represented in the bond line, not like the CH bonds. If you try to represent CH bond also by the same single CC bond, then you will be getting a different idea. So structure, carbon-carbon single bond, C double bond C. So number of sigma is going to be 3. Number of pi is 1. sp2 hybridization 120 degree is the bond angle. Shape will be trigonal planar. C triple bond C, C single bond C. How many bonds are there here?
2
2
sigma
sigma 2 pi
2 sigma 2 pi. Hybridization is going to be
s
sp
sp. And what about the bond angle 180 degree? And shape is going to be linear. What about in this case? C double bond C double bond C. 2 sigma 2 pi. Hybridization is sp. Like 2 double bonds are there to the same carbon atom. So the carbon atom itself is connected with 2 double bonds. Bond angle is 180 degree, and shape is going to be linear again. Shape will be linear again, right? So these are the different types of structures: sigma and pi bonds, hybridization, bond angle, and shapes. Let us proceed with the degree of carbon and hydrogen. So primary carbon or primary hydrogens. So what does it mean? Carbon atom attached to no other carbon or only one carbon is called as a primary carbon, or hydrogen atom attached with the primary or primary carbon. Like primary carbon, what is the primary carbon means? The carbon atom attached to no other carbon or to only one carbon. If it is attached to no other carbon, that is, it is called as methyl. Okay, there is a different case like methyl, and then primary, then secondary, and then tertiary. Methyl, primary, secondary, tertiary. These are different types of methyl, primary, secondary, tertiary. These are different types of carbon atoms, and we can say the hydrogens connected to that particular carbons are said to be methyl hydrogens, primary hydrogens, secondary hydrogens, and tertiary hydrogens. Secondary carbon or secondary hydrogen means carbon atom directly attached to two carbons. If a carbon is connected to two carbons, then it is said to be secondary. Or secondary carbon and the hydrogens connected to secondary carbon are said to be secondary hydrogens. Tertiary carbon means obviously the carbon should be connected to three other carbons. Carbon atom directly attached to three other carbon atoms is called tertiary carbon, and the hydrogens connected to that particular tertiary carbon, they are said to be tertiary hydrogens. Hydrogens connected to that particular tertiary are said to be tertiary hydrogens. Quaternary carbon means carbon atom directly attached with four other carbons, and quaternary carbon means that is a carbon connected to four other carbon atoms. In that case, there are no hydrogens connected again. Yes or no? There are no other hydrogens present in that particular case because already carbon has four bonds. This is how we can actually differentiate between primary, secondary, and tertiary carbon atoms. Try to solve how many primary, secondary, tertiary, and quaternary carbons hydrogens are present. How many primary are there, students? Look carefully.
One.
Yes or no? Primary carbons. Primary carbons. Like only one carbon is there or not? This is a carbon which is connected to only one other carbon. That is the primary carbon. Secondary carbons, how many are there?
6.
6 or 5?
5.
This carbon is actually connected to three other carbons. So that should be tertiary. So we have 5 secondary carbons. Tertiary carbons are going to be 1. Quaternary carbon is 0. And primary hydrogens are
0.
hydrogens connected to primary carbon. So 3 hydrogens. Secondary carbons are connected to, every secondary carbon is connected to hydrogen. So secondary hydrogens, total number are 5. Tertiary hydrogen is
0.
0. And quaternary hydrogen, there is no point of quaternary hydrogen because if there is a quaternary carbon, already all the bonds are going to be carbon-carbon bonds only. Hydrogens are not possible. Right? Try to answer this. How many primary, secondary, tertiary, and quaternary carbon hydrogens are present? Look at primary, secondary, tertiary, and quaternary and check out. So tertiary carbon is a carbon which is connected to 3 groups. So this is a carbon, right? And this carbon you cannot include as tertiary because it is only connected to 2 carbons. The other side is we have NH. So this is secondary, all these are secondary. And there are 6 secondary carbons. 6 secondary carbons or not?
Yes.
Yes or no?
Yes.
And try to figure out the primary carbons. So this carbon is primary because this carbon is actually connected to only one other carbon. This carbon is primary because it is also connected to only one other carbon. This carbon is primary because it is also connected to only the carbons which are connected only to one other carbon. They are said to be primary. So there are 3 primary carbons. How many hydrogens are there in those 3? 3 plus 3 plus 2, that is 8 hydrogens. So 3 primary carbons and 8 hydrogens are there. What about secondary carbons? 6 secondary carbons and secondary hydrogens are 5. Tertiary carbon is only this particular carbon. So these are all secondary. Write down. This is primary, this is primary, this is primary, this is tertiary. Tertiary carbon is only one carbon and tertiary hydrogens are only one. Secondary hydrogens are 5, primary hydrogens are 8. Everyone got this idea or not?
Yes.
Right. Classification of organic compounds. Organic compounds are broadly classified in 2 types, like open chain or acyclic or aliphatic, and a closed chain or cyclic. Open chain means there is no cyclic chain present. Acyclic or aliphatic, it all indicates open chain compounds. Closed chain means ringed compounds like cyclopropane, cyclobutane, cyclopentane, cyclohexane, cycloheptane. All those are ring chains. So if you have a compound like this, open chain, in that open chain you can have saturated compounds or unsaturated. That means you can have multiple bonds like carbon-carbon double bond or triple bond can be present. Only carbon-carbon single bonds can also be present. In the closed chain also we can have aromatic structure and heteroatoms can also be included. So these are the different broad classifications. Yes or no? Can be again saturated and unsaturated. Here also same. Heteroatoms can also be present. Heteroatoms can also be in rings. Closed chain or cyclic compound that is said to be homocyclic or carbocyclic. So what is homocyclic or carbocyclic? As I have told you, in the closed chain, yes or no? In the closed chain, ring is formed by carbon atoms only. If the carbon atoms alone they form the ring, then that is said to be homocyclic or carbocyclic. If the ring is actually formed by not only carbon atoms, but other than carbon atom, if there is an atom like nitrogen, oxygen, sulfur, in that case it is said to be heterocyclic. Like pyridine is example, pyrrole, furan, thiophene. These are all the examples of heterocyclic compounds. And cyclopropane, benzene, phenol, these are the example of homocyclic or carbocyclic compounds. Is that clear, students?
Yes, sir.
Yes.
Find the number of heteroatoms in the ring. How many heteroatoms are there in the ring?
3.
How many heteroatoms are there in the ring? If you look at the heteroatoms, like 1, 2, 3, 3 nitrogens are there. In the ring, we have 3 nitrogen atoms. So ring is formed by 3 nitrogens and 3 other carbons. So total number of heteroatoms is only 3. Here we have CH2, C double bond O, CH2, C double bond O, O. So how many heteroatoms are there in the ring?
1.
1.
One heteroatom is there in the ring. Yes or no? So because the other two C double bond groups, the carbon is actually doubly bonded with oxygen, but it doesn't mean like it is a heteroatom. It is still the carbon atom. So we have only one heteroatom, that is oxygen. Then comes the next concept like homologous series. A series of organic compounds having same functional groups arranged in increasing order of molecular mass. That is said to be homologous series, and the different members of series are said to be homologues. Like if you take alkanes, alkanes are homologous series only, because if you take the simplest alkane, you get methane. If you try to increase the carbon-carbon bond, like you get a ethane, then you try to increase, you get a propane. That means all these are just alkanes, but if you look at the change or difference between them, they are like higher members of the same type of functional groups, that is alkanes. So a series of organic compounds having same functional groups arranged in the increasing order of molecular mass, that is said to be homologous series, and the different members of the series are said to be homologues. CH3OH, if you take CH3OH, it is an alcohol. If you want to get a higher number, you have to add CH2. C2H5OH. From the C2H5OH, if you want to get higher alcohol, what you should do? You have to connect again one more CH2. It will be C3H7OH. Yes or no? CH3OH is an alcohol. If I want to increase the chain length, CH3, CH2OH. Further increase means CH3, CH2, CH2OH. Further increase means CH3, CH2, CH2, CH2OH. These are all said to be homologous series or not? So the successive members of homologous series, they are differing by CH2 groups or a molecular mass of 14. Between this CH3OH and between this CH3, CH2OH, this is the CH2 which is extra. So CH2 has a molecular mass of how much? Carbon will be having 12, 2 hydrogens is 2. So that means 14 units difference. Yes or no? The successive members of homologous series differ by CH2 or 14 molecular mass. The homologues have same chemical properties due to same functional group. Because of same functional group, their chemical properties are going to be same, but the physical properties, they are going to be different or not, students? Physical properties are going to be different because with increase in molar mass, what happened to the van der Waals force of attraction?
Increases.
Increases. So because of that, physical properties changes as van der Waals forces are directly proportional to molecular weights. Because as the molecular weight increases, the number of carbon-carbon bond increases. If the number of carbon-carbon bonds increases, there is a instantaneous dipole generated along with the dipole-induced dipole-induced dipole. There is a possibility of instantaneous dipoles generated. Because of that, van der Waals force increases. What is the general formula? CnH2n plus 2 is the general formula. In this, we will be having one pi bond. if we have one pi bond means what? CnH2n plus 2. It is general formula of what type of species?
Alkane.
Alkanes. From the alkanes, if we have one pi bond, that means we have removed two hydrogens. In that case, you will be having one pi bond means what type of general formula you will be having?
CnH2n.
CnH2n you will have. CnH2n can be for alkenes as well as for cycloalkanes. This is for cycloalkanes. Like whenever we have one ring, there also we have seen the loss of hydrogens, and it is also for alkenes. So general formula of alkanes is CnH2n plus 2, n is equal to 1, 2, 3, so on. So CH4 is the first member of the group. If you try to increase, then you will be getting C2H6, methane, ethane, propane, yes or no, butane, pentane, like that you will be getting all the heavier members. These are all said to be homologues. These are all said to be homologues. General formula of alkenes. What is the general formula of alkenes? CnH2n. So what are the alkenes now? Can we have an alkene with single carbon?
No,
Yes.
sir.
No, sir.
In the single carbon, there is no possibility of C double bond C. So there is no question of an alkene. So we should have at least two carbons, C double bond C. CH2 double bond CH2 is your alkene. And to that, I can actually increase one more CH2. So if I keep a substitution CH3, CH double bond CH2, that is C3H6, then C4H8. All of them will be falling under this formula CnH2n. Alkynes, what is the general formula? CnH2n minus 2. Here you can have one triple bond. Yes or no? CnH2n minus 2, and we can have the minimum number of carbons required for an alkyne to be possible is minimum number of carbon atoms. How many are required? 2 carbons. C2H2, C3H4. All of them will be falling under this formula CnH2n minus 2. C3H4, C4H6, C5H8. Yes or no? Is that clear, students? Alkanes, alkenes, alkynes formulas.
Yes, sir.
Yes, right. So let us proceed with the next general formula of alcohol. What will be alcohol? How the alcohol is generated? Like we have CH4. From the CH4, I have removed a hydrogen, loss of hydrogen, addition of OH. Then I'll get CH3OH. It is having CnH2n plus 2. I have removed hydrogen and I have added OH. What do you mean by this? Can I say from this hydrogen has been removed, so I can write CnH2n plus 1 and OH is added, so I'll write OH. Can I write like this? CnH2n plus
Yes.
1 OH. CnH2n plus 1 OH. So that is CH3OH, C2H5OH, C3H7OH. All these are different alcohols. CH3OH, C2H5OH, C3H7OH. General formula of ether. Ether will be having what type of formula? CnH2n plus 2O. CnH2n plus 2O. Because ether is actually like two alkyl groups are present on two sides of the polyvalent atom like oxygen. So you'll have first member CH3OCH3. If you try to increase the methyl group to ethyl, that means CH3, CH2 you have to add. You have to add CH3, CH2, OCH3, CH3, CH2, OCH2, CH3. These are different types of ethers. All of them will be having the formula like CnH2n plus 2O. Ethers again can be classified into symmetrical ethers and unsymmetrical ethers. Symmetrical ether means both sides you have same alkyl groups. Unsymmetrical means both sides you have different. One side you have methyl, other side you have ethyl means that is unsymmetrical. Both sides methyl or both sides same groups means that is symmetrical. General formula of aldehydes. Aldehydes will have what type of formula? CnH2NO. Because if we have CH4, we will be reducing that to HC double bond H. Yes or no? That means we have removed two hydrogens and then place the C double bond group. That means from the alkane CnH2n plus 2, we have removed two hydrogens. So you have made CnH2n, two hydrogens have been removed, and you have placed one oxygen. So CnH2NO, that is the general formula of aldehydes. Aldehydes and ketones are actually functional group isomers. So since they are aldehydes and ketones are isomers, they will be having same formula, same general formula. So in the aldehyde we have HC double bond OH, formaldehyde, then you can have acetaldehyde and all other compounds. In the ketone you have CH3, C double bond CH3. That means minimum 3 carbons are required to generate a simplest ketone. N stands for 3, but for formaldehydes N stands for 1. That means to the C double bond O group, if both sides, if you have alkyl groups connected, then only it is said to be a ketone. For that condition to be satisfied, it should be a if for C double bond O, if both sides we should have an alkyl groups, then that is said to be a ketone. So for that condition to be satisfied, we should have a minimum of 3 carbons. And then you have general formula of carboxylic acids. Carboxylic acids, how they obtained? Like CaH4. From this, if I want to remove HC double bond OH, that means I have removed two hydrogens and I have placed one C double bond and one OH. That means ultimately two hydrogens are retained and we have added two more oxygens, not one oxygen. Yes or no? C2, like if we try to figure out CH4, from that CH4, that one carbon is actually present and two hydrogens are present because we have added one C double bond O and COH. So C2H2O2, that means H2CO2. H2CO2. It is not C2 because we have only one carbon. We have two hydrogens, two oxygens. So with the one carbon also we can have a carboxylic acid that is nothing but formic acid. It has a general molecular formula of CnH2NO, CnH2nO2, and formic acid, acetic acid, all these are examples. Second member also you can write CH3, C double bond OH. Here we have two carbon C2, hydrogen should be 4, CnH2n, oxygen should be 2. General formula of carboxylic ester. Ester means you will be having HC double bond OCH3 or CH3 C double bond OCH3 or C2H5 C double bond OCH3 or OC2H5 or C double bond OR dash. R is an alkyl group. R and R are different. R and R dash are different alkyl groups. The general formula of carboxylic ester is CnH2NO2. CnH2NO2, where N stands for 2, 3, 4, because we require a minimum of 2 carbons. Why? Because in the C double bond one carbon is required, and in the OR dash one more carbon is required. Is that clear, students?
Yes, sir.
Yes, sir.
So these are all the different general formulas of different types of functional groups, and we all know that we will be studying about every functional group in your 12th standard, and in 11th standard we will be looking at all the hydrocarbons. Anhydrides, general formula CnH2n minus 2O3. So general representation will be C double bond O, C double bond O, H C double bond O, C double bond H. Again, if you try to add CH2, CH3 C double bond O, C double bond H. Again, if you try to add CH2, you will get CH3 C double bond O, C double bond CH3. So different anhydrides and their different anhydrides and their homologues have been written here. Different anhydrides and their homologues have been written here. And the general molecular formula is CnH2n minus 2O3. General formula of amines. Amines you can have primary amines, secondary amines, tertiary amines. Primary amines means we have NH2 group. Secondary means NH, RR dash. Tertiary N connected to 3 same or different alkyl groups. Quaternary amines means in that you will be having what? The nitrogen connected with 4 groups where the lone pair of electrons and nitrogen is used in the attack. So nitrogen should possess a positive charge. So representation of amine. RNH2 is the primary amine. R is a carbon atom. So CnH2n plus 3. CnH2n plus 3N. This will be the formula because from the NH2 we are adding 2 hydrogens. From the NH2 we are adding 2 hydrogens. CH3NH2 plus CH2 means CH3, CH2, NH2 plus CH2 again means CH3, CH2, CH2, NH2. CH3, CH2, CH2, NH2. All these are going to be the general molecular formula and the homologues of amines, primary amines. Cyanide means CN representation. So C triple bond, and whenever you try to add, we have replaced one hydrogen from the alkane. We have removed the hydrogen from the alkane and added C triple bond N. So CN H2N minus 1 and N is there, because you are not only added you have added CN means you have indirectly added carbon also. So number of carbons also change. So ultimate formula will be CN H2N minus 1 N. HCN, CH3CN, C2H5CN. Yes or no? These are the homologues. Homologous series of cyanides. Isocyanates will have the same type of general molecular formula, because cyanides and isocyanates are isomers. Yes or no? Isocyanates will be having CN H2N minus 1 N, HNC, CH3NC, C2H5NC. These are the different formula of isocyanates as well. Because isocyanate means nitrogen is actually connected to carbon. Cyanides means the carbon-carbon bond linkage is there. Is that clear, students?
Yes, sir.
Yes.
Yes, right. All these are basic formula and basic representations. So there is no difficulty part in this so far. Example 1, try to, which of the following compounds are homologues? Look at A and B, CH3, CH2, CH2OH, CH3, CHOH, CH3. Both are alcohols, but are they homologues? They are not having the increase in molecular mass, so they are not homologues. CH3O, CH3, CH3, CH2OH. There is a difference in the functional group, so not homologues. CH3, C double bond OH, CH3, C double bond CH3. There are difference. There is a difference in the functional group again, because first one is aldehyde, second one is ketone. If you look at D, CH3, C double bond OH, CH3, CH2, C double bond OH. Both are carboxylic acids. Just there was increase in the molar mass, so obviously D is going to be the right answer. Okay, same functional groups, and the molecular mass increased. Molecular mass increased. Common naming, let us try to understand. So there are two types of name, students, for the organic molecules. One is the common naming, the other is the IUPAC naming. Common names are also useful nowadays, because there are some molecules which are defined or which are derived very old, like they were in usage from long back, and in that at that time they have been assigned some common name to that. So that common name is still in use. So there are common names which you need to understand, as well as IUPAC nomenclature rules. And you don't mix up the rules of common names with the IUPAC rules. IUPAC rules are separate, different. Common name rules are separate and different. We'll be studying common naming first. First thing is common naming for hydrocarbons and hydrocarbon derivatives. Like hydrocarbon means alkanes, alkenes, alkynes. And derivatives of hydrocarbons means different types of functional groups you can have. Like you can keep the hydrogen replaced by OH or Cl or C double bond O. Like all the derivatives you can derive. All the functional groups you can add in the hydrocarbon derivatives. Hydrocarbons, alkanes, when more than one structure is possible from the same molecular formula, then we use N, iso, neo to distinguish between them. Like if you have methane, let us say, alkanes, right? First, methane I have second. If it is methane, there is no other possible way to represent the same methane. If it is ethane, CH3 single bond CH3. There is no other way to distinguish ethane again. If it is methane, ethane, you cannot distinguish again. After that, if it is propane, we can have CH3, CH2, CH3. Is there any other way to write the structure of propane?
Yes, sir.
What is that way, Faizan?
Propane,
Isopropane.
Isopropane you can write.
No, sir.
No, sir.
How can you write isopropane? We cannot write, right? Like we have, I either have to replace this CH bond either here or here. If I connect this methyl group to this carbon, it again becomes 3 carbons only. So there is no possibility of writing propane also. Propane is also N-propane only. So there is no possibility of isopropane. Like butane, you write CH3, CH2, CH2, CH3. Can I write the same butane in this fashion? CH3, CH, CH3, CH3.
Yes, sir.
So
Yes.
for butane, I can write. Difference is there for butane from butane onwards. Yes or no? N prefix is used if it is a straight unbranched chain. ISO is used when it, the molecule are CH3, CH, CH3 units. If this CH3, CH, CH3, this is units. If this unit is there, you use the ISO. Neo can also be used when the molecule has this unit. CH3, C, CH3, CH3, CH2 should also be there. This is your Neo unit with no further branching. There is some exception for this, we'll discuss that. Minimum 5 carbons are required for Neo prefix. Minimum 5 carbons because this unit itself contains 5 carbons. CH3, C, CH3, CH3, CH2. That unit itself contains 5 carbons. So minimum 5 carbons are required for using the prefix Neo. Try to name it C4H10. I am starting with C4H10. It is an alkane, CnH2n plus 2. Why I am starting with C4H10 directly? Because methane, ethane, and propane are represented only by one way. There is no other possibility to represent methane, ethane, and propane. C4H10, I can write all the carbons in the long chain or one of the carbon substituents. What is the name? First one?
Butane.
N-butane we have to write because all the carbons are the long chain. Second one name?
Isobutane.
Isobutane.
Isobutane because we have CH3, CH, CH3 group present. Right? Simple case. Then we have C5H12, propane. You can have all the 5 carbons in this fashion. You can have one of the carbon like methyl substituents. You can also have CH3, C, CH3, CH3, CH3. In that case, you have N-pentane, isopentane, and you can also have neopentane. N-pentane, isopentane, neopentane. So these are the different ways to represent the same, to represent different isomers of pentane. Exception is this case CH3, C, CH3, CH3, CH2, CH, CH3, CH3. It is said to be isooctane, even though we have neo group. Like when you are saying iso, when only this particular substitution is there and no other branching is there. But this was the exception. It is still called as isooctane. Even though we have neo type of substitution, it is called as isooctane. That is the exception which you have to understand carefully. Alkenes will have CnH2n molecular formula. In that, how we can write the names you can write. Common name of alkene, alk plus ylene. So alk refers to the number of carbon atoms. So how many carbons are there? That will be giving you alk scenario, that is root word, and you have to finally add ylene. So CH2 double bond CH2. How many carbons are there here? 2 carbons. So what should be the respective name of CH2 double bond CH2?
Dilene.
You can write ethylene. CH3 CH double bond CH2. Number of carbon atoms are 3 carbons. So propylene. CH2 double bond CH, CH2 single bond CH3. This is said to be alpha butylene. So you have to use, like in the IUPAC nomenclature, we use numbering. Here you use alpha beta to indicate the position of double bond. So CH2 double bond CH, single bond CH2, single bond CH3 is alpha butylene. And whenever you have a double bond with the second carbon, then it is said to be beta butylene. What is his name? CH3, C double bond CH2, CH3.
Isobutylene.
Isobutylene, very good. Isobutylene means you have, like earlier we have CH3 single bond CH, CH3, CH3. It is nothing but isobutane. But whenever you have an alkene, you have to replace the 2 hydrogen atoms, you have to remove and replace that single bond with a double bond. CH3, C double bond CH2, single bond CH3. You have to mention isobutylene. Alkynes, HC double bond CH, acetylene is the name. And you can have hydrocarbon derivative, students. System A, there are two systems, there are two types of derivatives. Whenever you have hydrocarbons, directly you can write N or iso or neo suffix. So using those prefixes, you can actually write down. But whenever we have derivatives, like from the hydrocarbon, you have replaced one of the hydrogen and added a halogen, or replaced some hydrogens and added a functional group. In that case, how to name? If it is hydrocarbon, you can use the prefixes like N, iso, neo. When it is a derivative of hydrocarbon, there are again two possibilities, system A and system B. System A is radical independent. System B is a radical dependent. There are two cases, radical independent, radical dependent. So we look at all the two cases. Radical dependent will be carbon containing functional group except ketone. All functional groups, all carbon containing functional groups except ketone, they are going to be radical dependent and they belong to system B. Carbon containing functional groups, they will be generally in system A except your ketone. Ketone will be radical dependent even though it contains carbon in the functional group. Cyanates and isocyanates can be named through both systems. You can name cyanates and isocyanates using both the systems, not an issue with the cyanates and isocyanates. Let us now look at the radicals. Radical means what? First, radical is not a free radical which you study earlier. You might have studied about free radical substitutions, free radical additions. So it is not that free radical. Radical is a substituent. It is a group which is obtained by removal of hydrogen from hydrocarbon. If we have methyl, like if we have methane, from that methane, if you remove the hydrogen, the methyl generated is a radical. Yes or no? Alkane minus H generates alkyl. CH4 minus H, you will be generating CH3. This is a methyl radical. CH3, from ethane, if you remove hydrogen, the generated radical is ethyl radical. CH3, CH2, CH3, from that if you try to remove hydrogen, you can remove hydrogen from the terminal carbon or from the middle carbon. If you remove hydrogen from the terminal, you will be getting CH3, CH2, CH2 dot. And what is the name said to be?
N propyl.
Yes or no? And you can also remove the hydrogen from this middle one. So if you are removing the hydrogen from the terminal, then it is said to be N propyl. If you are removing hydrogen from the like this middle carbon, like where you are generating CH3, CH3 group, it is said to be isopropyl. So these are said to be different kinds of radicals. We have many more. CH3, CH2, CH2, CH3. From here, I can remove hydrogen from where? I can remove hydrogen from this particular carbon. In that case, what I will be generating?
N-butyl.
N-butyl. If I remove from the terminal carbon, I can remove hydrogen from these two carbons. In that case, can I write isobutyl?
No, sir.
So what is that name? It is said to be secondary butyl. N-butyl and secondary butyl. You can also write the same compound butane like in the isobutane structure, like 4 carbon atoms, CH3, CH, CH3, CH3. Now here I can remove the hydrogen. If I remove the hydrogen, what I will be generating? I can generate isobutyl when I have CH3, CH, CH3 substituent is there. When this particular group is there, I can say isobutyl. When we have CH3, C, CH3, CH3, when this is the type of radical, that is said to be tertiary butyl. When this type of radical is there, that is said to be tertiary butyl. Everyone got this or not? How to name radicals?
Yes, sir.
Yes.
And this radical naming is going to be difficult whenever we go with the increasing number of carbon atoms. That is why this common names is not going to be useful greatly. IUPAC name is highly useful. These common names are only for specific type of compounds because we can't name radicals with the higher substituents. CH3, C, CH3, CH3. If you try to remove the hydrogen, you will be getting neopentyl group. Okay, those are the different types of radicals with the saturation where only carbon-carbon single bonds are there. We can also have unsaturated radicals. CH2 double bond CH2 group is said to be vinyl group. Like we have CH2 double bond CH2. The carbon atom of C double bond system, that is a vinylic carbon. If you try to remove hydrogen from the vinylic carbon, that is said to be vinyl radical. What is allylic radical? The carbon connected to the C double bond system, that is allylic carbon. If you try to remove hydrogens from the allylic carbon, that is said to be allylic radical. Some other radicals and their names. What is this radical? CH3CH. It is connected to substituents. Ethylidene, right? CH2, single bond CH2, two substituents are there. Ethylene, CH2, two substituents are there. Methylidene or methylene. It is said to be what? Phenyl group, pH. Toluene, from the toluene, if you try to remove one hydrogen, you will be getting benzyl. If you try to remove one more hydrogen, you will get benzol. If you try to remove one more hydrogen, you will get benzo. Yes or no? From the toluene, if you try to remove one hydrogen, you will get benzyl. From the benzyl, if you try to remove one hydrogen, you will get benzol. Like phenyl group connected to CH, two substituents. Phenyl group connected to carbon, where three substituents are there, that is said to be benzo. So these are some of the unsaturated radicals and their corresponding names. Is that clear, students?
Yes, sir.
Is that clear to everyone or not?
Yes, sir.
Yes, sir.
Yes, right. So do this example. Find degree of following radicals. CH3, CH2, CH2. Try to answer this question, all of you. All of you try to answer this question. Just a second. Yes, what was the name, students? So what are the names of these particular radicals? CH3, CH2, CH3?
N-propyl.
N-propyl.
Yes or no? N-propyl. And what is the degree? So this particular carbon is actually connected to only one more carbon. So you can say primary. CH3, CH3. It is nothing but the carbon is actually connected to two other carbons. We don't know what substitution is there. So with respect to carbons connected, we have to mention it. It is secondary. Yes or no? And it is, what is the name of this? Name of this radical?
Secondary propyl.
Secondary propyl or isopropyl?
I.
We have the system or not? CH3, CH connected to CH3 group. The system is there or not?
Yes.
Isopropyl. So then this one, CH3, CH, CH3, CH2 is there.
Isobutyl.
Isobutyl. What about here? C, CH3, CH3, CH3.
Neon.
Tertiary butyl. Here we have CH3, C, CH3, CH3. This is nothing but neopentyl. Yes or no? Hydrocarbon derivatives. System A, radical dependent. earlier whatever you have written. So one system is radical dependent, other system is radical independent. So radical dependent means, so you will be having this format of naming. You have to write radical and then you have to add the suffix. So system A is radical dependent for non-carbon containing functional group except ketone. For non-carbon containing functional groups except ketone, you have to use this. That means ketone is also going to be like a radical dependent only. Functional group halogen X, whenever it is there, you have to use the suffix halide. OH there means alcohol. NH2 NH there means you have to write amine. Whenever it is O, it is ether. C double bond O means ketone. CN means cyanide. NC means isocyanide. And the format what you are going to get is radical plus suffix. What is the radical name? And the suffix name is from these particular compounds like halide or alcohol or amine or ether or ketone or cyanide or isocyanide. And this is for non-carbon containing functional groups except ketone. For ketone, it is also radical dependent. For all other functional groups which contain carbonyl, it is radical independent. Try to name the compounds. CH3, CH2OH. What is the name?
Ethyl alcohol.
Ethyl alcohol.
So CH3, CH2 is ethyl group and OH is alcohol. So ethyl alcohol. Yes or no? So radical, we have to add radical and a suffix. So CH3, CH2 is ethyl radical and OH is alcohol, ethyl alcohol. CH3, CH2, CH2, CH3, CH2, 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 Cl. Radical, what radical? CH3, CH2, this is a radical.
N profile.
CH3, CH2, CH2, this is a radical. And the chlorine is the functional group halide. So N propyl, you have to mention N propyl chloride. N propyl, you have to mention carefully because you don't know the position where chlorine is substituted. If you didn't mention N. CH3, CH, CH3OH. What is this radical?
Isopropyl.
CH3, CH, CH3, OH. Yes or no? It is nothing but isopropyl group and alcohol, isopropyl alcohol. CH3, CHOH, CH2, CH3. What is this? It is not isopropyl, it is secondary butyl, secondary butyl alcohol.
Second.
CH3, CH2, CH2, CH2Br. It is nothing but N-butyl bromide.
N-butyl bromide.
Right? Very good. You try to answer from now onwards. What is the name of this? CH3, CH, CH3, CH2Cl.
Isopropyl chloride.
Propyl or butyl?
Butyl.
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 Isobutyl chloride. Okay. So look at the number of formats carefully. What about this one? CH3C, CH3, CH3Br.
Neobutyl
Neobutyl or tertiary?
Tertiary
Tertiary butyl.
Tertiary butyl chloride. Very good. What about this one?
bromide. Neopentylamine.
It is bromide, not chloride, because bromine is there. And it is going to be neopentyl amine. Right. What are the next compound? CH3O, CH2, CH3.
Methoxy.
ethyl methyl
Ethyl
ether.
methyl ether.
Ethyl methyl ether, because again based on alphabetical order we have written. CH3O, CH3.
Dimethyl ether.
Dimethyl ether.
Very good. CH3NH2.
Methylamine.
Methylamine. CH3NH, CH2, CH3. Ethyl methylamine. Very good. But whenever you're trying to name the secondary amines or tertiary amines in IUPAC nomenclature, there you can write N-methyl, N-ethylamines, N-common dimethyl amines. But here, whether it is a secondary amine or primary amine, just ethyl methylamine. CH3, CH2, NH, CH2, CH3. Diethylamine. Right, very good. What about this? CH3 and CH3, CH3. Whether you have primary amine or secondary amine or tertiary amine, it doesn't matter. Just amine is a suffix. And what is the radical? Methyl radicals. So how many radicals are there? 3. So trimethyl amine. What about here? CH3, CH, Cl, Cl.
Ethylidene chloride.
Ethylidene dichloride. CH2Cl, CH2Cl.
ethylene dichloride,
ethylene dichloride. pH CH2H,
benzyl alcohol,
benzyl alcohol. CH2 double bond CHBr,
Vinyl bromide.
vinyl bromide. Very good. So just radical plus suffix. That's it. CH3 C double bond or CH2 CH3.
Ethyl methyl ketone.
Methyl
Ethyl
ketone.
methyl ketone. Very good. CH3 C double bond or CH3.
Dimethyl ketone.
Dimethyl
methyl
ketone.
ketone,
Dimethyl ketone. CH3 CH2 CN.
Ethyl cyanide.
Ethyl
ethyl
cyanide.
cyanide,
Ethyl
Ethyl
cyanide. CH3 NC.
Ethyl isocyanide.
Methyl
Methyl
lysocyanide,
Very good. So these are all the names, students. You only answered all the common names. So just radical plus suffix. Yes or no? Hydrocarbon derivatives, there are set of functional groups which are going to be radical independent. There are some set of functional groups which are going to be radical independent. For that also, how to name? For carbon containing functional groups except ketone, because although ketone contain C double bond, it is going to be radical dependent. So these are the functional groups like acetic acid. Yes or no? Acids, acyl halides, esters, amides, aldehydes, cyanides and isocyanates. You can write O-nitrile, O-isonitrile. For acid, the suffix is ic acid, il halide, alkyl 8, ic anhydride, amide, aldehyde, O-nitrile and isonitrile. So this is going to be the way of naming your hydrocarbon derivatives which are radical independent. We look at those names. The format is going to be prefix plus suffix. Earlier we have radical plus suffix. Here we have prefix plus suffix. This will prefix will give what idea? Number of carbons including functional group carbon. Earlier, whenever radical independent, we have radical plus suffix. Radical, we have to name the radical name and then you have to add the suffix name. Here, there are radical independent functional groups which are radical independent. For them, you have to use prefix plus suffix. Prefix gives idea regarding the number of carbon atoms including functional group carbon. So whenever we have one carbon, you have to name form. 2 carbons, acids. 3 carbons, propion. 4, butyl. 5, valor. With respect to these names of the prefixes, you have to actually give the complete name. Number of carbons, 1 means form, 2 means acids, 3 means propion, 4 means butyl, 5 means valor, and then you have to add the suffix name. So let us look at naming. And some special names are CH2 double bond CHC is acryl, and CH2 CH3 CH double bond C, this is croton. Acryl is the name for this particular carbon if this is actually substituted, and this particular carbon if it is substituted, it is said to be croton. C star is the functional group containing carbon. C star is the functional group containing carbon. Let us look at the name, students. Functional groups, different names we are going to have. HC double bond OH. What is the name?
formic acid,
Formic
Yes
acid.
or no? Prefix plus a suffix. Prefix gives number of idea about the number of carbon atoms in the compound, including the carbon from the functional group. Suffix gives like whatever the functional group we have, that is ic acid. We have prefix. How many carbons? Only one carbon atom. So that is form, and it is ic acid, formic acid. CH3 C double bond OH. 2 carbons means
Acetic
acid.
acid.
acetic
acid.
acid,
CH3 CHBr CH2 C double bond OH. How many carbons? 1, 2, 3, 4. 4 carbons are there. You have to include the carbon of functional group as well. So 4 carbons means what is the name?
butyl.
Butyl
butyl,
and ic acid. But we have bromine also, right? On what position you have bromine? This is alpha, this is beta carbon. Yes or no? This is C double bond OH is the functional group. With respect to functional group, the next carbon is alpha carbon. After that we have beta. After that we have gamma. So on the beta carbon we have bromo. So beta bromo butyric acid. CH3 CH CH3 COH. What is this? 1, 2, 3. How many carbons are there?
4.
We can use isobutyric acid. Although you say it is radical independent, we can use isobutyric acid because It's like how many carbons? 1, 2, 3, 4. 4 carbons are there. If we have 4 carbons in the straight chain, then that is said to be N-butyric acid. If one of the carbon is present as CH-CH3 group, then it is said to be isobutyric acid. CH3, C double bond OCH3. What is the name? CH3, C double bond OCH3. Methyl acetate. Yes or no? Because if you look at CH3, C double bond OCH3, this is nothing but your alkyl. Alkyl group is methyl group here. Methyl CH3, C double bond 2 carbons means acids, and 8 should end with 8. Methyl acetate. HC double bond OCH double bond CH2. What is that going to be? HC double bond OCH double bond CH2.
Ethyl formate.
This is nothing but a vinyl group or not? CH double bond CH2.
Yes.
It is nothing but vinyl group, and we have only one carbon in the HC double bond O, so vinyl formate. CH3 C double bond NH2. What is the name? CH3 C double bond NH2. These are amide systems.
Methyl.
How many? We have to use methyl, or how many carbons we have to count and then use acid?
2 carbons.
Prefix plus suffix, right?
Methyl.
So prefix and prefix, you have 2 carbons. 2 carbons acid.
Acetamide.
Acetamide.
Acid.
HC double bond H. 1 carbon. Form. It's an aldehyde. Formaldehyde.
Formaldehyde.
Right? Try to name this. CH3 C double bond H. One to two
Acetaldehyde.
carbons.
Acetaldehyde.
Acetaldehyde. Very good. CH2 double bond CH, C double bond H. This is a special case, right? Whenever we have CH2 double bond CH, C double bond H, we can use acryl. Acryl aldehyde, right? CH3 CH double bond CH, C double bond H.
Proton.
Protonaldehyde.
Crotonaldehyde. Very good. Crotonaldehyde. CH3 C double bond O, C double bond CH3. C double bond O, C double bond is zinc anhydride. You have to use the name acetic anhydride because you have how many carbons? 2 mother carbons, leaving out the C double bond O, C double bond O. So 2 carbons means acetic anhydride. Is that clear, students? Everything so far?
Yes.
Yes, sir.
Yes.
Try to name this. CH3 C double bond O, C double bond H. CH3 C double bond O, C double bond H. It is named as acetic formic anhydride. If you look at a C double bond O, C double bond O, it should be just ec anhydride, but the two sides we have different functional groups. Two sides we have different types of alkyl groups. One side we have methyl, other side we have hydrogen. So with respect to this CH3 C double bond O, you have acetic. With respect to C double bond H, you have only one carbon, that is said to be formic. So acetic formic anhydride. Like earlier, with respect to CH3 C double bond also, we have 2 carbons. CH3 C double bond also we have 2 carbons. So that is said to be acetic anhydride. But here we have, with respect to one side, we have CH3 C double bond 2 carbons. With respect to other side, we have 1 carbon. So acetic formic anhydride. CH3 C double bond Cl.
Acetyl chloride.
Acetyl chloride. CH2 double bond CH, C triple bond N. Vinyl cyanide you can say, because CH2 double bond CH is vinyl group, or you can also say vinyl cyanide you can use by that radical dependent system. As we have said, the cyanides and isocyanates can be named by both the systems, radical dependent or radical independent system. You can also say this carbon is acryl carbon, so acrylonitrile. Is that clear, students? Everything so far? So this is how you can actually name the compounds using common names or common system. This is how the naming of compounds can be done using common system. Then comes the naming of compound using here IUPAC nomenclature. Format for IUPAC naming. secondary prefix plus primary prefix plus root word plus primary suffix plus secondary suffix. This is the format for IUPAC naming. For your radical dependent, we have radical plus suffix. For radical independent, you have prefix plus suffix. That is for the common systems. But IUPAC has been given some set of rules to follow and name all the known compounds so far. So you can use the system, students: secondary prefix, primary prefix, root word, primary suffix, secondary suffix. Secondary suffix gives idea regarding what type? Can anyone say? Root word gives idea about what? Root word gives idea about the number of carbons in the parent carbon chain. Primary suffix gives idea about the type of carbon-carbon linkages. Secondary suffix gives idea regarding the type of functional group. Primary prefix gives idea regarding the whether cyclo groups are there or not. Secondary prefix idea regarding the substituents. Okay, it will give idea regarding the substituents. Primary prefix cyclo, if it is there, you have to add number of carbons,
Number of carbon in parent carbon.
type of carbon linkage. Secondary suffix will be giving idea about
Principal functional group.
principal functional group. Right? So these are the names. Like secondary prefix, if you go with the secondary prefix, substituents are written along with their locant positions in the alphabetical order. If you have R, it's said to be alkyl. If you have CH3 methyl, C2H5 ethyl. X means halo, like F means fluoro, Cl means chloro, Br means bromo, I means iodo. NO2, OR, CH, OCH, N double bond O. All these are substituents where the respective primary prefixes, secondary prefixes are being given in this manner. Methyl, ethyl, fluoro, chloro, bromo, iodo. NO2 is nitro. OCH3 means methoxy. OC2H5 means ethoxy. Epoxy, CH, OCH, that will give you epoxy. N double bond O is nitroso. These are always treated as substituents in IUPAC nomenclature. If these groups are given to your students, if these groups are present to you, they are always treated as substituents. They are not considered as functional groups. But there are some set of functional groups which are also treated as substituents. Like if in the molecule we have more than one functional group, then one is the principal functional group, other is the substituent. So other has to be the secondary suffix. So if these groups are there, they are always substituents. Okay, format for IUPAC naming: secondary prefix, primary prefix, word root, primary suffix, and secondary suffix. Primary prefix means secondary suffixes we have given earlier substituent names. Primary prefix means if the compound is cyclic, then you have to use the prefix cyclo. Word root means it gives the representation regarding the number of carbon atoms in the main chain. How many carbon atoms are there in the main chain? That will be given by root word or word root. Number of carbon atoms, if you have one carbon atom, what is the root word? We have meth, 2 carbons, eth, 3, 4, like that. If you try to increase the carbon atom, you will be having this particular root. 3 means prop, 4 means but, 5 pent, 6 hex, 7 hept, 8 oct, 9 non, 10 dec, 11 undec, 12 dodec, 13 tridec, 14 tetradec, 15 is going to be pentadec. These are the root words for different types of different number of carbon atoms. And in the format again, you have secondary suffix, secondary prefix we have given substituents. Primary prefix we have given type of cyclic linkages. Root word, number of carbon atoms. Primary suffix denotes whether the compound is saturated or unsaturated. That is type of carbon-carbon linkage. If you have single bond, we use the word ane. Carbon-carbon single bond means ane. Carbon-carbon double bond means ene. Carbon-carbon triple bond, when it is present, you have to use ine. So ane, ene, ine, these are the primary suffixes you have to use whenever you have different types of carbon-carbon linkages. Like we have carbon double bond carbon, C double bond C, single bond C double bond C, adiene, C double bond C, C double bond C, enine, C double bond C, C double bond C, adiene. And secondary suffix will give idea regarding the principal functional groups based on priority table. Okay. So we have to use the secondary prefix first, like whatever substituents are there. Then primary prefix, if there is a cyclic group, cyclo you have to use. Root word, number of carbon atoms you have to write. Then primary suffix, that is type of carbon-carbon linkage. Then secondary suffix, writing the principal functional group. And based on priority table, we will be giving the principal functional groups all. So this priority table we will discuss in the next class. Okay. Priority table, what is the functional group we can give? Based on that, based on all these only, you are going to write the different IUPAC names for different types of organic compounds. Is that clear, students?
Yes, sir.
Yes.
There are some compounds where some special secondary suffixes we are going to use. We'll be discussing all that in that list. Right? Thank you all. We'll discuss
Thank you,
tomorrow.
sir.
Thank you, sir. Thank you, sir.